So in part B of this question, we are asked to consider the interval where point S is at 1/2 d over here, and we need to state in which way the induced current is induced. So what we know is that when the loop is going into region 1, the magnetic field is increasing and is going out of the page. Therefore, the induced current, according to Lenz's law, will have to oppose this change. So the induced current's magnetic field has to increase into the page. So the exact opposite of what is happening is trying to counteract, which is the essence of Lenz's law. So if it's into the page, we can use our right-hand rule. We place our thumb pointing into the page, and we see the rest of our 4 fingers curl this way, which is clockwise. And then in part 2 of this question, we need to derive an expression for this induced current in terms of R, D, V, B, and B. And so what we know according to Faraday's law is that the induced EMF is the negative rate of change of flux. Again, this negative sign corresponds to Lenz's law. And while the rate of change of flux can be rewritten as the time derivative of B times A, as the flux over here. And well, what we can say is that the area, this will be d over dt, the area is simply d times x. So that's how much, so the x coordinate represents how much of the loop is inside of the region. And well, b and d don't change with respect to time. Therefore, those are just constants and we don't need to take the derivative. So this will just be bd times dt dtx. And well, this here is just the velocity of the loop. Therefore, this will simply be b negative b dv b dv. Just like this. And what we know is that current is voltage over resistance. Therefore, we can simply plug these values in. So this will be the current. And then in part 3, we need to get an expression for the power dissipated. Well, we know power is equal to I squared times R. So we know our current, B dV over R squared, multiplied with R. And this will simply be B squared, D squared, V squared over R.